So with our infinite limits, we're going to have an infinity in here. And what this means as x approaches infinity. In other words, as x gets really, really big, what happens to x squared? It's going to get really, really big as well. All right, if you plug in a big number like, what's a big number? A billion. If you plug in a billion, then you have to do a billion squared. What's a billion squared? A billion squared. Well, a billion already has 9 zeros. So how many zeros would you have if you squared it? 18. So you can go to, here I've got on my board here, I've got a chart, I think I got it in grade 5. So 18, it's going to be 1 quintillion. Because it tells me if I have 18 zeros, it's a quintillion. Yeah. So if you have 45 zeros, it's a quattordecillion. Make sure you know that for the exam. Okay? So, yes, if we plug in a billion, we get a really big number. So big we have to go to a special green piece of paper that we've owned for like 25 years just to check what it's called. So what we write, and what we're going to write, to be specific, is we're going to write infinity, because this gets really, really big. What your textbook is going to write in these cases is they're going to write, since it's not actually a number, they're going to write does not exist. We're going to be a little bit more specific than our textbook, because we're going to want to tell if it goes to infinity or to negative infinity, whether it gets to a really big positive number or a really big negative number. So what happens here? If x gets to a really, really big number, this one is going to get to a really big negative number. And it doesn't have to be x's that we're dealing with. We can have different letters. What happens is n gets to a really big negative number. Can you see that this one is going to be negative infinity? And of course, your textbook for all of these would say does not exist. Now I'm going to put an example underneath here for this. If we pick a value bigger than 1, so let's go limit as x goes to infinity of any number 3 times x, and we're picking a number bigger than 1, like 5. Anytime that happens, does that make sense that this is going to go to infinity? As long as a is a positive number. Of course, if I made the a value in front a negative number, it would go to negative infinity. Now what yes?
Going back to the one.
Yeah.
If it's an even number, would it turn infinity into a positive number if it was negative?
So now, even if I had a negative here and I had x to the 4, okay, this 4 is applying only to the x, not to the negative.
That's what I'm asking. If infinity is negative.
If infinity is negative, so this one's going to be negative infinity, but if I had this limit as x goes to negative infinity of negative 3, well, I don't need brackets there, I'll write it exactly the same. And 3 is positive? So in this case, this power of 4 is going to make whatever is in there positive, times by a positive 3. This one will be positive infinity. So we're really thinking about what happens if I put a big number in there. Is it going to get big or not? And is it going to be positive or not? Okay? Here, now we have 1 over n. What's going to happen if we put a really big number into this one? It's going to get smaller. Okay? And it's going to get closer and closer to 0. So here's a real life example. You have one birthday cake, and it's your birthday. You want to share it with all your friends. Unfortunately, the amount of friends on Facebook has been approaching infinity because you just keep getting more and more and more. How much cake does each person get? Because you have to split it up, right? Just it gets smaller and smaller and smaller the more friends that you have, right? So if you really like cake, don't have friends. You can just have the whole cake to yourself. So in this case, as this gets bigger and bigger and bigger, you're getting closer and closer to 0. We can see these things on our graphs. Like on this one, let's start with the x squared one. If we think of our x squared graph, well, our x squared graph looks like this. And as you keep going this way, you can see that the graph keeps getting bigger and bigger and bigger. But if we would go to this one that we just did, where it was equal to 0, and we think, what does that graph look like? My 1 over n graph, or 1 over x graph. My reciprocal graph looks like this. What happens as x gets bigger and bigger and bigger? You can see it's getting closer and closer to that asymptote, and it's getting closer and closer to 0. You wouldn't have a hole at 0 because this one is getting closer and closer to 0, and even at your x value, as it gets closer to 0 for x, 1 point it goes up, 1 point it goes down. So we would say the limit this one does not exist. We wouldn't even write infinity or negative infinity because as we come from the left, if we come from the left side of 1 over x, we get negative infinity. But if we come from the right side, of 1 over x, we get positive infinity. So because these two don't match up, we would say our limit doesn't exist. Here, these are zeros. So now I'm looking at what happens as x gets closer to 0 on this graph. So I'll just draw my little point to drag it along there. If I come from the left side, can you see that it's getting closer to 0? It keeps going down further and further and further. That's why I would say negative infinity from the left side. But if I took this dot and put it on the right side of my graph and got closer and closer to 0, it goes up forever. So that's why I would say from the right side, it's equal to positive infinity. And since the left and the right don't match up, we're going to say that it does not exist. Again, your textbook would say does not exist if it does go to infinity. Just as something that's different, remember we looked at our volcano graph the other day? No, that was a different class. Do you remember your volcano graphs? Oh, that's another mathematical term, of course. That would be a 1 over x squared graph. Your 1 over x squared graph has an asymptote here and an asymptote here. And because it looks like a volcano, sometimes we call it a volcano graph. There we go. Well, this one, if we come from the left or we come from the right, what happens? It goes to positive infinity both ways. So we could say that that limit is equal to infinity. It's going to equal 5. Because what happens is n gets to be a really big negative number. That fraction will become 0. And then 5 minus 0. Yes, that's where you, it's a calculator question, of course. That's where you plug it in and you find out, yes, yeah, it is. It's 5. Good. So in general, any time that we're going to infinity, and we have any kind of power on the bottom, and we got to change this because it doesn't quite match. What letter should I have here? It should be an N instead of an X. That's going to go to 0. Now for these ones, I'm going to show you a technique, and then I'm going to show you a shortcut for figuring these ones out. But there's a little bit of algebra that we can do here. So when we look at this, we're going to factor out the highest power out of both the numerator and the denominator. And it's not the highest power in the numerator and the highest power in the denominator. We look in the whole expression and say, what's my highest power of n? It's n to the 1. So if I factor out an n out of the top, and I factor out an n out of the bottom, we're going to see what happens. Now, you're going to say, well, according to my normal rules of factoring, you can't factor the top, Mr. JR. You can't factor the bottom, really. There's nothing, there's not a common factor of an n in there. Well, let's expand a little bit and say, well, let's say we try to. What happens if I take out an n, I force it out of the top? I'm going to be left with 2, that part's easy, plus what? What would be here if I factored an n out of 2n plus 3? N times what would equal 3? 3n to the negative 1, or 3 over n, right? Does that make sense? So normally we wouldn't have been allowed to factor that out, but if we stretch our rules a little bit, yeah, it works. And there's really nothing to factor out on the bottom because it's just n. Well, if you did that, what have you done? You've just changed what this expression looks like because our n's are going to cancel out. And so now our expression becomes a limit as n goes to infinity of 2 plus 3 over n. And it looks like what we were doing before. What happens to 3 over n? It becomes 0. And so this limit, 2 plus 0, just becomes 2. Let's try the next one. Try a couple, and then we'll look at a shortcut. The highest power in the whole thing is n cubed. So we're going to take an n cubed out of the top, and we're going to take an n cubed out of the bottom. What would you have to multiply n cubed by to get n squared? N to the negative 1, or 1 over n. And then here, this would be easy. It would just be minus 3. On the bottom, you would have 8 plus, and if you took an n cubed out of there, you'd have n to the minus 3, or 1 over n to the 3. And now our n to the 3's will simplify. So now we're left with the limit as n goes to infinity of 1 over n minus 3 over 8 plus 1 over n cubed. And this is going to equal 0 minus 3 over 8 plus 0, or negative 3/8. So this would be the math that you would show to see why that it works. Now, what happens as n gets really, really big, especially with powers? would you agree that n cubed is more powerful than n squared? It goes up faster. And n to the 5 is more powerful than n cubed, and n to the 10 is more powerful than n to the 5. So when we look at these questions with powers, with an expression, a polynomial on the top that has powers, polynomial on the bottom, we're really only concerned with the most powerful thing. Everything else can be ignored. So in this expression, the most powerful thing is an n to the 1. And there's 2 of them on top and 1 of them on the bottom. And if you just thought about that, the limit would be 2. On our second one here, the most powerful thing is n to the 3. And if you just ignored everything else, because once things get really, really big, it doesn't matter those other things. It's like playing Monopoly. At the end of the game, if someone lands on one of those very first ones, Mediterranean or Baltic, and they owe you $2 for rent, at the end of the game, you're like, don't worry about it. It doesn't matter. Because you're already dealing with amounts of money that are so much bigger. At the beginning of the game, it's important. Because you're like, I need that $2. I'm going to win. Yes? So on a test, if you just said, well, the biggest power is n cubed, so I can see that this is -3/8, I'll be okay with that. And you just write down the answer. Of course, if you write it down wrong, then you'll lose all the marks. So this would be how you would show your work to get through it. So now we can do stuff like yeah. There isn't an n to the power of 9 on the top. No, you're going to use n to the power 9. How many n to the 9s do I have on top? None. How many n to the 9s do I have on the bottom? 1. What's this limit? 0. Okay? Because what would happen is if you factored out an n to the 9 out of everything, you would be left with the same kind of idea. This whole thing is going to act very much like 1 over n, because there's one more n on the bottom than on the top. If I did this same question, but made this an n to the 18 on the top, now my biggest power is n to the 18. I have a lot more n's on the top than I do on the bottom. And as n gets really, really big, this will equal infinity. Of course, if I had an n to the 18 on the bottom, now I have the same on the top and the same on the bottom. I really only have to look at those two, and my limit's going to be 3. So that's a shortcut way of looking at it, because with powers, only the one that's biggest is going to affect things when you get to infinity or negative infinity. And so now you're thinking, well, what is it? Which one is acting that way? I'm going to do infinity or negative infinity? Ooh. Is it going to be, well, it's an odd number on top, but is it going to be infinity or negative infinity? Okay. It's going to be negative infinity. If I change this to n to the 8, Would it stay the same, or does that not matter? Doesn't matter. Okay. You're right, it's still negative infinity. If I change it to n to the 7, does it stay the same or does it not matter? This time, it's positive infinity. What just happened? Two negatives make a positive. If we think about the top, when I plug in a huge negative number, is going to be negative because of the end of the 13. That end of the 13 is going to make a huge negative number. On the bottom now, my end of the 7 is going to make a pretty big negative number, but not as big as the one on the top. And a negative divided by a negative would be positive. Whew. A little bit of abstract thinking there. What happens to this as n gets really, really, really big? As n gets big, it's either going to be odd or even. It's just going to keep switching between the two, right? Can you see that then the answer switches between being positive 1 or negative 1, positive 1 or negative 1? So we would say since it's not getting closer and closer to a certain value, it keeps switching between the two. This one does not exist. What's this equal to? You're saying it's equal to 0? You just grouped. If you group everything together like this, you agree it's equal to 0, 0, 0, 0, 0, 0, 0, all the way along, so it should equal 0? But if you moved, if I just get rid of those brackets, what happens if I grouped it like this forever? Then all those are zeros, and I started with 1. So then it should be equal to 1. So this sum doesn't exist. We can't say what it's equal to because it keeps flipping between equaling 1 and then equaling 0, then equaling 1 and then equaling 0. So even though you could group it together and argue, well, I group them all together and I just am adding a bunch of zeros, so it should be 0. You could also group it all together and say I'm just adding a bunch of zeros to 1, then it should equal 1. Things get a little bit sometimes fuzzy when you work with infinities. What about this one? As n gets really, really big. It's going to go to, you see it equaling 0. Okay. And if we go to our example that we started with talking of limits, and I reminded you of geometric sequences, and I started 16 away from the wall, and then I walked half the distance, so I walked 8 plus 4 plus 2 plus 1, so on and so on. And we're like, you were first introduced to the idea of limits in geometric sequences. Here are r values a half. Now, if you would go back to your formula sheet in grade 11, you have a sum of the first n terms of a geometric sequence.
Pardon the interruption. Can we please have all the students that have volunteered to be hosts for a team picnic
As this.
come down to the front of the office for their meeting? All the individual students that have agreed to be hosts, please come down to the front of the office. Thank you very much.
Well, if we plug in things here, We have a problem. How do you do 1/2 to infinity? Well, 1/2 to infinity is exactly this idea that we're talking here. It's going to equal 0. So this just becomes that. And you learnt the formula for infinity was just t1 over 1 minus r. Well, that was because this limit, this part, equaled 0. And that's why the formula changed from what was the formula for the first n terms to the formula for the infinite amount of terms, which is pretty cool. What have we got? One more note and one more example. So this is from geometric sequences and geometric series. Whenever this r value, and again, we got a notation switch up here, change that to n. Whenever that r value is less than 1, like 1/5 to the power n or 2/8 to the power n, that limit's going to equal 0. And so, in our last example, what's going to happen here as x gets close to 0? This is one we did before. This one does not exist, remember, because it went from the left side, it goes down to negative infinity, and from the right side, it goes up to infinity. But the basic idea is when you divide by 0, you get a very, very big number, either positive or negative, depending on whether the fraction was positive or negative to begin with. All right.